No? Okay.
So, you want to give
cheers.
your comment?
Thank you. Okay, so this is, I suppose this is just for the recording, or are there actual speakers in the room? I'm not sure. Just for the recording. Okay, fine.
And one other thing, when somebody asks a question, please repeat the question for the recording.
Passed.
You good to go?
Yeah, I think I'm fine.
All right, well, thank you very much, everybody, for coming back from lunch. First up, we've got Vedran talking about, well, a route towards quantum-enhanced intelligence.
Yeah, so first of all, many thanks for the very kind introduction. I was pleasantly surprised to be invited to talk here. Specifically, when I saw the list of speakers, I was like, wow, it's very flattering. The original title is A Route Towards Quantum-Enhanced Artificial Intelligence, which I slightly tweaked a little bit here, so it's kind of in the direction. The reason is, I submitted the title and I regretted it instantaneously because machine learning, AI is a horribly overloaded concept, right? So I suppose I want to spend a few minutes telling you what I will actually be talking about and what I will not be talking about. And I'll be using it as quotations of this guy here, who is called Justus Piata. This is a robotics professor at Innsbruck, whom I had the pleasure of working with a little while. And last week we had a conference on machine learning in Innsbruck. And he was talking about robotics stuff, and he gave this working definition of artificial intelligence from his classical perspective. He says that it's an unsuccessful meta-science that spawns successful scientific disciplines like machine learning and automated theory proving and things like this. Because there's this fundamental problem that once we know how to solve a problem, we no longer consider it to be a test of intelligence. For example, when Deep Blue beat Kasparov in 1996 and we started producing more and more algorithms which are producing superhuman performance in chess, we were reluctant to call this intelligence, right? It's just an algorithm and we know how it works, we understand it. So it's somehow never going to happen. AI is always one level beyond. But so there's this open-endedness question of AI. But on the other hand, I don't know if you know much about history of AI, but there were these AI winters. AI was a verboten concept in a way. But recently, since we've had successes in optical character recognition, driving, etc., now AI is becoming a positive buzzword. So suddenly we're in a situation that not only can AI be reached, but everything is AI. So I'm kind of stuck between these two extrema. Is everything AI? Is machine learning AI? Or nothing? None of it is AI. So here's a sort of a Venn-like diagram of what I want to be talking about. So the topic of the conference is quantum machine learning. As you know, it is an emerging field, somewhere containing the intersection between machine learning and AI on one hand and quantum information processing on the other, containing some stuff which might be beyond both. And what I want to talk about is sliced by the concept of reinforcement learning, which is one particular mode of learning that I will tell you about for some 15 minutes or so. And there's going to be a part which is beyond from the perspective of textbooks of reinforcement learning. So now it's not really conventional machine learning, and it's reinforcement learning, and it's a bit beyond. So I said, let's call it AI. And I'm taking it back. It's reinforcement learning plus. So this is the topic. Please do interrupt me. Please tell me to slow down. I might not listen to you, but I will do my best. So the topic really has three parts, because there are three things that I want to tell you about. One thing is about classical reinforcement learning, sort of what are the bottlenecks, why we want to do it, etc., in the case you're not well familiar with the topic. The second part is about one possibility of how quantum machine learning, quantum effects might help in reinforcement learning type problems, which is maybe slightly different than what you're accustomed to, which you have seen at the conference. And third part, this is sort of an independent topic that I like a lot. It's about using small quantum computers to solve computational problems, which I will somehow force that it really belongs in this entire thing. And you will be kind and you will agree with me that yes, it makes sense to present all these things together. And hopefully each one will take 15 minutes and I will be done in time for questions. I will do my best. Just as a maybe brief reminder for those who are new to the field, what is machine learning? When I say machine learning, I mean one of three things, two of which are here. One is supervised learning, the other one is unsupervised learning. Supervised learning is about learning from labeled examples. I'm trying to infer some conditional probability distributions of labels given data points. assuming that I'm given samples from some empirical distribution. So this is, the physical law, the real world, if you wish, which generates these examples. And for me, I would like to just point out this concept. It's somehow about generalizing knowledge. We know stuff from the examples, and we generalize over it. Unsupervised learning, we had a very interesting discussion about what unsupervised learning means. What does it mean to learn without supervision in any possible way? But here, typically people talk about two aspects of unsupervised learning. One is discriminative, where you're trying to identify some properties of the distribution from which your examples come from, like bimodality, that it has like two clusters. Or sometimes you talk about generative models where the task is to somehow guess what the underlying distribution is, or rather to generate new samples given a bunch of examples. Right? So you somehow guess the distribution and you generate new examples. So I will say roughly this is about generating knowledge. I just need these buzzwords, generalize and generate, for later on. It's not necessarily true. And the third canonical mode of learning, and now we're no longer in all machine learning literature. So far, that's all machine learning literature, now in like 30%. In 30% of machine learning literature, you're also going to hear about reinforcement learning, which is somehow different. In reinforcement learning, just to get the jargon down, we talk about an agent who exists relative to some task environment. It perceives the state of the environments by using its sensors, so it perceives the world around it. It acts upon it by producing actions, thereby changing the state. And to make it reinforcement learning, time and again, there's a signal, usually called a reward, which somehow tells you intuitively whether the performed action in the given situation was correct. This is how you train a dog. Like most of little baby behavior is learning of this particular type. And it's become very popular. So in like 2015, nobody knew about it. And then came AlphaGo. Now everybody knows about it. And it's MIT's hit technology of 2017. And I will not advertise it more for you guys. I think you don't deserve it. You've been very nice. But I will be a bit more formal. Not that I need all these concepts, but it's going to make this concrete for you, I'm hoping. One very specific type of reinforcement learning, the first thing you will see in more mathematical literature, is reinforcement learning which deals with a specific subclass of environments. These environments are called Markov decision processes. So here environments have a certain number of states, usually a finite number of states, like S1, S2, S0. The agent can see the state of the environment. And once an agent performs an action, there's a transition of the state happening within the environment. The transition is guided by the action, but it's not necessarily deterministic. So if the agent does, in this example, action A not in state S1, it deterministically transitions to S0. However, action A1 is probabilistic, and you might end up in S1 or S2. Okay? So the final component of a Markov decision process is a reward function, which simply specifies that certain transitions, so action, state triplets, are rewarding. So you did the right thing. If you started here, did this action, and end up here. Okay? It's a mathematical object item, a pentuplet, if you wish. Once we've fixed what an environment is, we can fix what an agent is. Well, whatever it is something which at any point in time has a specified policy. This is just fancy speech for saying there's some function which specifies what the action will do given a state. Is this clear? I'm writing it as a conditional probability distribution because the output might be stochastic, right? It doesn't have to be deterministic action given a state. So once I fixed a specification of the environment and once I fixed a policy, well, now I can start writing things down, like how well I'm performing. I could, for instance, write expected rewards as a function of time. I can sum up all the rewards up to some time step t. This is now finite horizon rewards. Or I could, for instance, consider infinite horizon rewards where I depreciate the reward at every time step with respect to some geometric function. So this gamma is some real number between 0 and 1, so this goes to 0. As long as my rewards are upper bounded, this will converge. Now, once I fix my favorite figure of merit, I can talk about optimal policies, right? So policies which achieve the best possible behavior in this given environment. And down the line, this is what reinforcement learning is about. One technical distinction: if you give me the specification of the environment, like you give me the transition function explicitly, and I'm asked to compute the optimal policy, this is usually called sequential decision theory. If you don't give it to me, but I can access the environment, like really do an action, see what happens, and then I'm doing reinforcement learning. Okay? Now, this all seems very simple, but it turns out that even this very simple case of reinforcement learning, when I'm trying to achieve optimal behavior in certain classes of environments, is not that easy. There are many, many methods that people have considered. If you want to use it in reality, then you encounter immediately problems like the fact that your State spaces are infinite, like in vision, it's effectively an infinite state space. My actions are continuous. I don't necessarily perceive the entire state of the environment, just some property, right? I don't know exactly what you're thinking, but I see what you're doing. Sometimes I care about reaching certain goals in the environment, certain states in the environment, and I don't care about particular transitions. I might want to transfer knowledge, plan, and I like to think that reinforcement learning is something which connects other more data-oriented machine learning techniques to something which should be AI, like it's sort of a bridge. At least if you think about robots, like embodied intelligence. Now, further, just to make you feel more comfortable with reinforcement learning, I would like to contrast supervised learning to reinforcement learning because there are some similarities and there are important differences. They're quite easy to highlight. In particular, this act of learning an action in a given state, which is down the line what the agent has to do to identify the optimal policy, is somehow similar to learning a label given a data point, right? Which is what you do in reinforcement learning. That is the case. This is very similar. What is very different, however, is how the data is accessed, right? I don't have a bunch of examples given beforehand. I have to generate them by acting. So it is not IID. It's not independently distributed. I'm not learning a distribution. I'm learning some sort of a process. The examples are provided implicitly. I'll come to this in a second. So it's similar, but then also dissimilar. Let us consider an example of chess. So I can learn chess using reinforcement learning. If nobody told you the rules, this is exactly what you would do. The state space of chess as a reinforcement learning problem are all the legal configurations of a board. The transitions of the actions are what move I can make. Like, so it's some kind of a tree structure. But it's not a tree, right? I can come back to the same board position in which I was before. It happens often in chess, in fact. Further, I don't really know whether my move was correct, right? It's not a labeled example because, you know, suppose you win a game and then you ask yourself, well, was the move 47 in my 68 move game the right one? You don't know. Your adversary could be bad. So this is the so-called problem of credit assignment. You're not sure what was the right thing to do in a given time. And just as a minor remark, purely technically speaking, mathematically speaking, you can embed supervised learning, things like oracle identification, many standard computation-like processing tasks in a Markov decision process. You can rephrase everything as a reinforcement learning problem if you wish. However, this is usually the stupid thing to do. Usually, if there is no structure, if things are provided ID, there are much faster ways to learn. So reinforcement learning is in many ways the hardest way to learn. Okay? But magically, I mean, in recent times, we have huge progress in reinforcement learning. I'm fully aware that most of you know details of AlphaGo and how it works. Hands up who doesn't know how AlphaGo works?
Are you talking about AlphaGo or
Yes.
AlphaZero?
Whichever one you choose.
No, because the AlphaZero was the one which won without knowing the...
Sure. Whichever one. If you started AlphaGo, you down the line understand the basics of what I need. But have you seen this example of navigating a city? Who has seen this one? Yeah, this is an interesting example of the expert, of course. But this is an interesting example where they trained an artificial agent, a learning agent, to go from place A to place B, which was specified by a frame, like a first-person view in Google Street View. So the agent navigated the virtual world by going up, left, right, backward, forward in Google View, and learned how to navigate cities. So for me, this is a mind-boggling thing from the point that we actually have the data to do that, which is insane, to the point that this thing solves the vision problems and solves implicitly some, I don't know, traveling salesman problem. It's a fascinating result. And I will come back to it later on a little bit. So let's talk a little bit about how you go from this picture which you had with 3 states where there are a couple of transitions, that's all you need to know, and it's still a hard problem to navigating a city. Or rather, how do we learn from interaction with an environment? Well, if I do pure reinforcement learning, like so-called tabular reinforcement learning, I can only ever learn what to do in a situation which I've encountered before, right? Now think, I mean, there's like 10 to the 172 legitimate board configurations in Go. You will never see 2 board configurations twice, except maybe for the first 3 ones, and that's it. Then you get lost in combinatorics. So what do we actually do? Well, we generalize over personal experiences. We kind of do the similar, we try to do similar things in similar situations, whatever similarity means, right? Still, unlike in big data, where supervised learning is sort of the king, The training set here in real-life reinforcement learning is still a negligible set of examples. We see very few things with respect to how many things we know how to do. So what we actually do, so this is sort of a working hypothesis, we generate many fictitious experiences, right? So for instance, when you're playing chess, this is a planning problem, you kind of think, okay, so if I move here and my counterpart moves here and then I move here, I kind of predict a few moves. Maybe I do it a couple of times, do something called Monte Carlo tree search, and then I opt for the best option. But none of these moves actually happen. It all happens in my head. So this is some kind of a generation of things. Yeah, if you want to know more about why I'm saying tilted face, you can ask me later on here. So I like this because it kind of suggests that this generalized reinforcement learning unites various aspects of learning. So it has this reinforcement learning flavor, the tabular reinforcement learning in the old school reinforcement learning, which is slow and few data points. Then it gets improved by adding something which is supervised learning like when I start generalizing. And even further, if I want to do really well in unpredicted situations, I have to generate new stuff, which is kind of like this generative flavor of unsupervised learning, right? Yeah. And this is the second slide which I'm asking you to somehow take into your mind. The first one is the first slide that is shown with Justus Piata. This is the second slide, and they're the most important slides in my talk, and they're not mine. So have you seen the cake picture before? Hands up on this. Good, I'm very happy about that. So there's a guy called Jan LeCun, who is one of the founders of deep learning. He's a very, very important scientist, a very cited scientist at that. He had this sentence which was all over the media. He said that if intelligence was a cake, then unsupervised learning, generation of stuff, is sort of the body of the cake. It is the cake itself. Supervised learning is the glazing on the cake, and the reinforcement learning would be the cherry. I'm not sure what he exactly meant by this, but you know, this is difficult to get to. You have to work really hard to deserve this one singular cherry at the end of your cake. But most of the stuff that is actually happening is in the body. And in fact, we know least about how to do generation properly in standard machine learning, in conventional machine learning. It's a really, really hard task. There's been progress, however, at least with respect to the generalization aspects, as exemplified by AlphaGo, both AlphaGo, the original one, and AlphaGo Zero, and AlphaGo Master, all of them, and then the generalized version with the shogi. So from early on, people have realized that you can do function approximation to generalize the policy. So the policy is not a tabular object, but becomes parameterized like a neural network, where you train the parameter rather than just the table entries of what to do in a given situation. And starting from linear models down to deep learning methods, which brought about AlphaGo when combined with more standard strategies. Now, in fact, my talk, what I want to be talking about today, and I think I'm going to say this in 2 slides, but I don't remember my talk anymore, is that I want to try to talk about generation. And I'm not being very specific what I mean by generation in the context of reinforcement learning. It's not necessarily a well-defined concept, but I'll give you 1 or 2 examples of what I mean. I mean things like this, like when you have a learning agent which is somehow trying to understand what it would do relative to a model of the environment, and it uses this to optimize its later on performance. Why I want to do that? So I had very nice slides. So here I had some car crash from GTA with a hammer. It was everything was destroyed. This is a real live car crash. Both these things should be without any sort of a license, so I can present them. We want to generate stuff and want to simulate stuff because getting experience from reality is expensive. Best example being automated cars, right? We don't want to necessarily learn from actual car crashes, even though this is going to end up being unavoidable, even in automated cars. So what I would really like to understand is things like this, like learning models where you have a simulated environment in which an agent trains, which is not identical to the actual environment we want to subject the agent to, but has some common factors, before it gets sent to another environment, which is the real environment. Like imagine, pre-training the Mars rover in a simulated condition, which is mimicking Mars as well as we can mimic it, as much as we know about it, before it gets actually sent to Mars. So these things there are many classical concepts associated with this picture here, like hierarchical learning, where I'm building up more complex skills from simpler skills, and transfer learning. This is the specific thing I'm showing here, where learning in one domain is somehow exploited to speed up and improve performance in another domain, right? Which are similar but not the same. human behavior, human knowledge, our levels of cognition could not be possible without transfer learning. We transfer all the time. This is why we can do what we do, not just on the level of the individual, but on the level of societies. Like, this is what culture does. We don't have to really learn things from scratch. We can be taught. Now, this pre-training stage, it will have at least two flavors, and you do it in two different ways in practice. One is by reinforcement learning. So you really play reinforcement learning with the simulation, but reinforcement learning is slow, so it takes time. Alternatively, you can somehow try to analyze the environment using clever optimization techniques. So not learn, but just analyze, because you have full access to it, like to the full matrix specifying everything that can happen. And both are computational bottlenecks. And I want to talk about quantum enhancements, or potentials for quantum enhancements under some conditions in these two domains. So how do we do that? First part of the story is about quantized environments and how reinforcement learning can be done faster in somehow quantum accessible environments, with the idea that these are going to be simulations. I will talk as if they're not, as if they're physical objects, but I will mean simulations. And the second part is just going to be set solving, which is, well, you can map anything onto set. Right. So what was our question? We wanted to somehow make sense out of what reinforcement would look like in a fully quantum domain. What would that mean? So we simply generalized the concepts of agent and environment to familiar quantum information theoretic terms. It's essentially a two-party communication scenario, right, where you have two separate registers, the register of the agent and the environment, and a communication channel. And the agent and environment are nothing but collections of either completely positive or unitary maps, it doesn't really matter, which act interchangeably, right? So they're the parts of the agent which are not accessible to the environment, and vice versa, and there's a part of the world which is the interface accessible to both. And whatever I can ever hope to describe in a two-party turn-based interaction, it fits in this picture here. In particular, so does reinforcement learning, and I can make it formal. I can restrict these maps to be somehow classical objects in a well-defined sense and recover all the classical reinforcement learning results. What could I want to improve? In general, there are two things that we care about in reinforcement learning. One is computational complexity, so the speed of my algorithm, how long does my algorithm take, and learning efficiency, which is essentially in one-to-one corresponds to query complexity or sample complexity in conventional computing theory. So I'm caring how many interaction steps with the environment I take before I start performing well with respect to whatever figure of merit I care about. And one trivial observation, which, I mean, it's a theorem, but it's a very simple one. If there's a classical filter between the agent and the environment, so if there's something continuously measuring the channel, right, then I can never hope for genuine speed-ups with respect to learning efficiency. Simply because whatever quantum scenario you invent, I can classically simulate here with exponential slowdown, but still I will not see it with respect to just the number of interaction steps figure of merit, right? In other words, and you cannot groverize a phone book. It doesn't work. You have to put it in a quantum computer first. So this is sort of what we did. We sort of asked, okay, so how can we get some meaningful improvements when I add somehow cues to these things in a systematic way? The motivation was actually to somehow realize that oracular computation is this part which is environment-like, which is the unknown oracle, just like in reinforcement learning, the environment is unknown. It has the agent-like part, which is a program which accesses this and learns something about the oracle or the environment, maybe using quantum effects. And the idea is to get the relevant information somehow faster. So, of course, the problem is environments as these infinite sequences of CPTP maps. Yes?
So I've got a question about the setup here. So the way you're thinking about it, are you imagining a policy being stored by a classical computer, or is policy stored by a quantum machine for this version?
You're asking whether the agent is classical quantum? The agent will be a quantum device.
Okay. So then in that case, I guess my question is, if the policy is stored in a quantum device,
yes,
then how does the agent use the policy that they've learned without observing it and degrading it?
I'm not sure if this answers your question, but down the line I will be producing actions in superposition, and I will cheat such that I get back coherent information. I will purify the entire process, which is not purified otherwise.
Okay.
Can I give you? I'll give you a concrete example.
All right.
So maybe
I'll
then you
bug
ask.
you later then.
No, but it's important, right? It's important to be upfront about what are the hidden assumptions and how this is meant to work. So down the line, I will actually not use reinforcement learning here. I will learn some property of the environment which will help me optimize a classical model for that family of environments, and this will be the trick. Right, so just wanted to point out that technically environments contain many oracular examples of special cases, like standard oracle identification or metrology or Elitzer-Weidman bomb tester. All these things can be rephrased as special cases here, and they're very degenerate compared to what we actually have in mind. So we came up with a process which systematically turns certain types of environments into some useful oracles with a bunch of assumptions we have to assume. Assumptions which we have to assume. My God. Anyway, so let me give you an example. So here's a real task environment. It's a maze. It's a very simple maze I stole from a master's thesis of a student because it's difficult to recreate. It has 5 different states, which are sort of rooms. And the agent is placed in the room A. It can move left, right, up, down. And there's some, periodic boundary condition saying that if I go up, I end up in A. And there's the room which is the rewarded one, which is room star. The corresponding Markov, there are many ways to write down a corresponding Markov decision process of this thing, but here's one, which is just marking down everything that can happen, right? But let me write down what the interaction looks like. So the agent perceives the state A, then does an action right. The environment computes what's the next state given the action, outputs the next state, etc. You see what I mean? I'm going to rewrite the same process in a different language, but it's going to mean exactly the same. So this object here is calls the causal map. I just put the agent on the left-hand side, its actions. The environment is in the middle, and then what the agent sees comes out on the right side. See, this is the same thing here, just unraveled in a different way. Time goes up, down, same as here. And now I can look at the fully quantum model for the same thing. So I have the actions plugged in here, and the states come out here, and there has to be something happening here to make this entire process down the line unitary when I purify the picture enough. So this is sort of the story. This is the agent part. This is the agent input, agent output, and there's something happening in the environment. Now, fine, and this is somehow capturing everything that I would want an environment to be, but it's somehow not what you want when you're thinking of using quantum oracles. Because what I realize is a mapping which goes from action states to state states with some information about whether I got rewarded in the end, plus a system which might be fully correlated here, which is not held by the agent anymore. So in fact, I could have a language where states and actions are the same symbols, and there's some bijective function between them. In this case, if I were to trace out this, whatever I plugged in superposition would simply completely dephase. So we get a classical mixture out. What I really want is something like this, right? Something which flips a bit if I did the right sequence of actions. And then I could Groverize the thing. So long story short, the entire process of oracleization has 2 parts. One part is this blocking part where I realize that multiple actions can be taken in one block, plus the part where I get a purification of my process. I cannot do it with real environments, but I can do it mathematically. And I call the process oracleization. And it has this blocking part which connects to things which are called quantum comms. And it has recovery and recycling, which is sort of an inverse process of recovering a unitary map from a CPTP channel. So it's the dilation theorem in action, if you wish. So once you do these things, you get some very simple results. For instance, I can do Grover-like amplification to find winning paths. And you can mathematically identify classes of environments in which having a quadratic speed up in finding the winning path for the first time, so this is unstructured search per construction of the problem, I can lead to whatever type of speed up in learning you want from that point on. But down the line, the true speed up here is quadratic, right? Because I'm using Grover. You can do similar things for, you can use any of your favorite classical quantum optimization algorithms to find optimum of some hyperparameters of your learning model. So it's all just about rephrasing things properly in this particular picture here. Then you can ask, okay, so it's just Grover type speedups that can get. And the answer is no. In fact, you can get whatever speedup you like in a very boring way. Well, why? Because I mentioned at the very beginning that reinforcement learning is such a broad framework that whatever problem you give me, I can encode it as a reinforcement learning problem. And we did that. We exemplified, in fact, here with Jake Taylor and where are you? With Wu. I'm sorry, I'm confused. First name? Chino. Thank you. And Yika Liu. My apologies. We exemplify this on Simon's problem. So Simon's problem is one of the oldest problems in quantum information where you can prove an exponential separation between classical and quantum computers under a promise that your function comes from a well-defined family. And we found a way of one-to-one encoding Simon's problem in a very convoluted Markov decision process. And then further, we realized that you can actually add some parts to it, some degeneracies, which include certain random hops, etc., such that two things hold. Adding this stuff didn't help a classical agent, and the quantum algorithm still works. So this is somehow finding the border of how far we can go away from standard or regular problems in this larger domain of reinforcement learning and still maintain classical quantum separation. So down the line, the hidden shift in the assignment problems becomes a key to learn some particular environment. Yeah, with technical things. So let's talk about, again, I had a nice picture of an elephant in a room, but it's copyrighted, so this one is not. There are a couple of obvious questions, right? Like one question is how far can I push this towards something new, right? I'm here just recasting well understood problems into a new language, and I agree, this is what we do. We extend it a little bit, and it's an open problem to see whether it actually makes sense in any realistic scenario. We would like to understand that. And you can also be critical about, okay, but wait, what about this oracleization thing? Real environments cannot be oracleized. Maybe they can if I'm a quantum experiment. If I'm talking about a couple of ions talking involuntarily with another couple of ions, then everything is purified by the construction of the experiment. But more importantly, what I really care about is this is an intermediary step in this training phase. Right? So the dream would be to somehow come up with a, there's something called Open AI Gym, where you can train and benchmark your AI algorithm one to another. Let's make it a quantum thing, right? So maybe you have a quantum database which encodes certain behavioral environments, which I can pre-train my models on. And then the speed up would really be in how much time do I have to spend here in the pre-training phase. And sometimes you can get exponential speedups with respect to this. Not in the real environment. This comes later when I send the probe to Mars. So to summarize this part of the story, quantum accessible environments can be turned into useful oracles under certain assumptions. And then I can use standard quantum information tricks to somehow gain a learning advantage. Now, of course, before we jump to conclusions and say that, well, maybe I have some sort of a speed up here in terms of reinforcement learning, I'm in a black box model, right? The fact is, if you really give me full access to an environment in a way which allows me to do this quantum oracleization, it is not clear there's no more clever classical algorithm to do the same. I'm not claiming that. I'm just saying if you have a black box, then you can encode these speedups.
So I have a quick question.
Sure.
So when you're talking about the silence problem format as the reinforcement learning,
Yep.
have you actually tried to use classical reinforcement learning to
So it's simpler than that. So you make the problem such that in order to get for the word for the first time, a classical agent takes exponential time.
I mean, have you tried numerically?
No.
So you just, I'm just curious, if you try it numerically, well, that would be always exponential time for like average cases?
So now the average case here is defined under whatever measure you need to make Simon's problem hard for classical computers. So somehow by construction it has to be hard. If you tell me, no, let's say the distribution of instances comes from somewhere else, I have no clue what happens, right? Sure, if you restrict your set of Simon's instances to something much smaller, then there are certainly classical algorithms which are going to work fast. But this is not about reinforcement learning per se. This also holds for Simon's problem.
Okay.
If you start restricting the family, then it becomes easy at some point for sure. Yeah, but I think the underlying question of, okay, what does this have to do with the real world? It's a fair question, absolutely. Okay, so now I have 15 more minutes, let's say, for the talk, and I'm going to segue into something completely different, right? It doesn't really fit in this paradigm. I could present it as a separate talk. It's about solving satisfiability problems on a quantum computer. But for me, it really does connect to the first story. It connects here, right? When I say that you train in a model and then you do something outside, and I mentioned that there are sort of two different ways how to do it. One is by playing reinforcement learning. The other one is by doing some optimization. And I'm skipping ahead. It turns out that many problems in learning theory are at least NP hard. Like in reinforcement learning, finding a goal-achieving policy is NP hard. In supervised learning and computational learning theory, which you'll hear about next, there are many instances of problems which are NP hard. Unsupervised learning, finding low temperature states of restricted balls machines are NP hard. And in game theoretic problems, things are NP hard all the time. In fact, it turns out that really interesting questions are beyond NP. They're p-space complete and x-time complete and even undecidable. But I will focus on this NP question, and I will ask whether quantum computers can help here. Now, of course, you know very well, yes, people have studied NP problems on quantum computers from the very beginnings, and it was one of the basic results of quantum information that it is unlikely quantum computers can solve these things in polynomial time for the worst case instances. So it's a fundamental question. Perhaps one of the reasons why it's not as studied as certain other problems, it's because we don't expect to see exponential separations. So it's not really elucidating BQP versus BPP, which is the question of quantum information, some would argue. But there have been results continuously, right? And let me contrast now these NP problems. And I'm using this sort of as a shorthand for saying, well, the types of problems I will encounter if I want to do reasoning in AI. I will continuously be encountering NP-hard things, which I will continuously be tackling with heuristics. It is unavoidable. Versus quantum-enhanced machine learning. So in quantum-enhanced machine learning, in models where there's an oracle, like a quantum database, we have hope of exponential separations, right? No back-to-back, what is it? Entry to exit proof of something like this, but we have very nice working examples. Further, I've heard this in this conference alone many times already, in one day. There's this intuition that we all share that since machine learning is about handling noise, this might be the right application for noisy quantum computers, right? It somehow matches very, very well, plays well. And we have examples where you can exemplify this. It's almost like quantum smoothing theory, specifically for quantum state preparation for quantum linear algebra. On the other hand, NP problems only allow polynomial speedups, and there's no reason to believe they're in any way well suited for near-term quantum computing. I think I have to put a caveat here. It's not entirely true. People who play around with annealers would say, no, no, no. They're exactly the thing to do, but they're hard to grasp somehow with conventional methods to understand what is happening with these algorithms. So I want to tackle this in a slightly different model than noisy quantum computers, and they're just small. So I'm not going to say that they're reasonable, a reasonable assumption, but I'm going to say, let's assume that my quantum computer is very small. How small? Let's suppose I want to solve a problem that requires n qubits, but I only have m, where m is much smaller than n. And the question is, what can I do? And it turns out, it's not a formal claim that I'm making, but it's an intuition. I will fight for it. Sometimes maybe I cannot do anything, right? If I want to factor a very large number, but I have a quantum computer much smaller than the square root of the number, intuition says this is not going to help me, right? Not even if it costs one step to factor this thing. Why? Because good algorithms exploit the problem structure. And if I chunk it into small parts, I kind of break the structure, so the overall performance has to suffer somewhere. So there's some notion of a threshold happening here. And the entire talk is actually about thresholds for one specific quantum speedup of one specific set-solving algorithm, which is a de-randomized version of Schrödinger's algorithm. And this is the remainder of the talk. I just want to come to an example where I highlight this threshold phenomenon for one case. So here's a three-set problem. We're talking about the problem of finding a satisfying assignment of a CNF formula. So we have a number of clauses. Each clause is a logical statement which contains a number of variables or the negation of the negations of a variable, 3, connected by a logical OR. So there's only one unsatisfying assignment per each clause, but I have a number of clauses and I have to satisfy all of them, right? And this is the canonical set question. Can I find a satisfying assignment for these things? And in like 1999, I think, Schrödinger came out with a very simple algorithm which does it. He said, pick a random assignment and check if it's satisfied. If it is, output that and we're done. If it's not, find the first clause which is not satisfied and flip one bit at random. Note, if I flip one bit, that clause becomes satisfied because there's only one unsatisfying assignment over 3 bits. And do this 3n times. So it's a gently directed random walk in the space of assignments. So he proved that this algorithm will find a satisfying assignment if one exists with probability 3/4 to the n. Note, a random guess is 1/2 to the n. So this is better than a random guess. Now if I iterate the algorithm until I succeed, the expected time until I make it is 4/3 to the n, which I'm going to write as 2 to the gamma n, where gamma is some number below 1, right? This 0.415. So if I were to do brute force search, the gamma, the rate of the algorithm is 1 for brute force search. Good. How do I improve this quantumly? In 2004, Ambanis pointed out that any such sampling algorithm can be improved by purifying the entire picture instead of classical sampling, doing amplitude amplification to do it. In which case I get a square root on the performance, so my gamma becomes gamma half. It's a near generic thing you can do, and the fact is we don't know much better than that, not for set solving. How many qubits do I need for that? Well, I need 3n qubits just for the purification of the randomness. not to mention everything else. So much, but I have m, which is much smaller than n. So what can I do? Well, one thing you might try, and this is going to be my example of a threshold. It is not the best one. There are many others, but this is the easiest one to explain. Well, one way I can shrink a formula. How? By setting a certain subset of the variables. Is, I guess, a part of the assignment, and this shrinks the formula to whatever number of variables remain. So here's my algorithm. I guess n minus m variables, and I solve the resulting m-sized formula on a quantum computer. Now, of course, if there's only one satisfying assignment, in general, I have to repeat this 2 to the n minus m times to find a satisfying assignment. This is the worst case scenario that I care about, right? So how fast is this? If I express the ratio between the size of the instance I can handle versus the size of the instance I want to handle, you get an expression like this. So it's some interpolation between 1 and n with the weight alpha, where alpha is the ratio. However, classically, I can do it with 2 to the gamma n, and gamma is not 1. So it turns out this is an inequality which you can solve, and for Schoening's algorithm, you get a number, 0.03 n. If my quantum computer cannot handle an instance which is larger than this, I actually have a quantum slowdown. So this is because this guessing of the n minus m variables, this is brute force search. So I'm interpolating between the stupidest algorithm I possibly can and the quantum enhanced algorithm, but the classical algorithm is still better than the stupidest one. So there's going to be a threshold happening here. Note, threshold effects happen all the time. Whenever you come up with a faster algorithm and you say you're going to ignore prefactors, edit effects, etc., there's some number which says my instance has to be at least this large before quantum speedup kicks in. This is different, right? This is a scaling statement. It's a statement about the ratio of the size between the quantum computer and the instance before I can get any speedups. And we tried many other ways of somehow chunking up the problem, and we always get thresholds. So then we ask, can we do it ever? Like, is there any way of doing it? And I have now 5 minutes to quickly sketch out how you do it. Our statement is that if you're trying to quantum speed up an algorithm which doesn't use too much randomness, and it recursively calls itself on a smaller instance, and if the subroutines or itself does not depend on the original problem size, then you can do it. That's the end result, explained on the example of Schoening solving. So there is something called de-randomized Schoening. So the original Schoening algorithm uses a lot of randomness, but you can de-randomize it, essentially by splitting the space of possible assignments into R balls. So you have a bunch of centers, and you look at balls which are radius R with respect to the Hamming distance, so there's the number of bits where they differ. And you sequentially solve the question of whether there's an assignment which is satisfying my formula within a given ball. It turns out that you can fully de-randomize Schoening and get the same runtime by such a deterministic algorithm. So now I've reduced Schoening to the promise ball SAT. Note the radius of the ball will actually be a fraction of n, which fraction is not particularly relevant, but R depends on n. Okay, so let's just keep that in mind. So I've reduced Schoening to promise ball SAT, which is a type of a local search procedure. It turns out to be the case, and I will not have time to go into details, that it has a recursive call on a promise ball where I fixed one of the bits. So at every call, every subsequent call in the recursive tree, I reduce the formula size by 1. And I can make it non-recursive, which saves me a little bit of space. What it turns out that then we can employ what we call a hybrid approach. A hybrid approach simply says that I will simply do this recursive tree, where I'm calling the algorithm on an ever smaller instance, until the time where my call becomes so small that the quantum computer can handle it. And then instead of calling the quantum routine, I call classical subroutine, I call the quantum subroutine. And as long as my quantum computer is somehow proportional to the size of the instance, I get a speed up. I get a smaller rate, the gamma, which is the figure of Mary that I care about. It is not entirely trivial, not even for this particular case, because of certain technical reasons. In particular, I need to keep track of which variables I'm flipping. I need to down the line somehow keep stored R variables. And you get in trouble because if you store your variables as an ordered list, so I have n variables, so I need log n to specify which one I'm flipping, and I need R of them to specify. It's R times log n bits that I need to store. If you do it like so, even though this looks like very efficient, n appears only as a logarithm, it turns out that as my instances grow, I'm losing all my speed up. And in the limit of infinite m, I'm not gaining over a classical algorithm. If I try to store it as a set, so forgetting the order somehow, well, then I'm in trouble because my step, which has to be reversible because I want to quantize the entire thing, it becomes irreversible because I'm forgetting which was the element that I added to the set last. So the question is there any way of somehow keeping reversibility and keeping low storage? There's something called algorithmic deletion. You can delete information by rerunning the algorithm backwards. For this particular case, it turns out this will be exponentially slow. But there's a different way, a way of splitting memory in some sort of a recursive tree where you store sort of an exponentially growing tower of bits in a very efficient way. And it turns out that the algorithmic deletion over such a structure becomes exponential in the log of the depth of the tree, not in the log of the tree, not in the tree itself. So it turns out this is time and memory efficient. Yeah, so that means that given a quantum computer of size m, where m is a fraction of the instance size, I can actually solve promise ball with a speedup. And putting it together with the old algorithm, you get some kind of a total complexity thing, which says that, so this thing here is the fraction of the size of the quantum computer and the instance that I have. This is a constant with respect to n, whenever m is a fraction of n. And it's coming with a minus sign over the classical rate. So this is a polynomial speedup. And it doesn't depend, I mean, the size of speedup does depend on the ratio, but doesn't depend on the scaling of the instance. So it's a genuine speedup, no matter what the ratio is. So the point where I would somehow wrap back on the quantum conspiracy that quantum algorithms are maybe somehow good because of noise is right here. So right now I'm saying these types of problems, NP complete problem, yeah?
So remind me again, is M the number of clauses?
No, M is the number of qubits I have access to. So N is the number of variables, number of clauses is poly N.
Okay.
Okay, so here's the final statement. The types of problems I care about in AI are either machine learning problems where we feel there's some sort of an algorithmic conspiracy happening, or NP-hard problems. NP-hard problems seem to have a lack of structure in the algorithms which solve them, which I can exploit to use small quantum computers and gain an advantage. So it also has a flavor of the right application for near-term quantum computers, especially when I combine it with the fact that in fact in AI I don't care about finding optima. I don't care about finding satisfying assignments. I really care about finding things which are close to satisfying assignments. So piling more arguments that machine learning or AI is maybe the right set of apps for near-term quantum computers. And I would like to thank a bunch of people from Innsbruck, where I started doing quantum machine learning through NIST and JQI with Jake, Jenny, and Yikai. And the last work was with Ignacio and Ge at Max Planck. And this is a reminder, there was a little bit about pre-training, like transfer learning, a little bit about local search, and something about classical agents and quantum environments. And that's it. Thank you. That's the end of the story.
All right, thanks a lot for the great talk. Questions?
You said you want to be resistant to noise for a SAT, right? And you said like maybe you want to do some optimization. So why did you look at like max SAT?
It could also be
many clauses?
So the question is, if one cares about optimization and one wants to be remaining somewhat close to SAT-solving algorithms, why not try to find solutions for max SAT? It's a very good question, and we should look into that. It is not the case that I'm saying that SAT-solving is resilient to noise. I'm saying that if NP-hard problems occur in machine learning, it is likely that we don't really need to solve those things, but some bad approximations thereof, and still gain an advantage. But definitely max SAT is something we want to try. But I'm thinking that whenever you can apply local search strategies, our tricks are going to work. So you'll be able to use smaller quantum computers.
Any other questions?
I just had a comment. So if you look at SAT competitions where people actually run these Schoening type of algorithms, so I mean, if you look at Schoening's algorithm, he runs a quantum walk, which is like a classical walk for 3n steps, and he repeats that exponentially many times. But it so happens that in the SAT competitions, they run an exponentially long walk for polynomially many times.
But they don't do that, right?
Yeah, actually, they do that in SAT competitions.
Oh, but they don't run anything. I mean, they don't run anything exponential long because their instances are like millions.
Sure. But I mean,
So maybe the point of the question has to do now with how is SAT solving actually done in practice on large instances in SAT competitions.
Exactly. in that case, I mean, how do you compare, like, it's not clear to me how you, like, it seems like what you do, you improve what's happening within the subroutine, the walk statement, right? But so your improvement will be larger if the walk happens for a longer number of steps.
But bear in mind, the number of steps here is still smaller than what churning needs.
Oh.
Right, so now we're talking about sort of details of various types of random walk solvers.
Great.
I have to say, in fact, churning modifications are pretty bad, right? This is not what you do in set solving. The heuristical algorithms are these DBLL type algorithms which are looking for bounded width resolutions. And what is worse, portfolio solvers, which combine a bunch of techniques in a messy way. So I'm not claiming anything in that direction, but this is where I really want to go, right? I really want to see what quantum computers can do for these things, which solve, including uncomputable problems in practice, like verification, right? We do it. We don't do it for all instances, but we don't see all instances.
Okay, just talk offline.
Sure.
Any further questions? All right, well, if not, let's thank our speaker.
Thank you.
Now, I believe have a break right now.
Very short break.
Very short break now.